Welcome to the series of e-learning modules on problems with quantity discount. By the end of this session, you will be able to explain the use of inventory control models to determine how much to order or produce and when to order or produce, and also to explain inventory models that allow quantity discounts. Let us first start with an introduction. In many situations, suppliers give discount on bulk purchase. In such cases, the unit cost of inventory is not constant as it is dependent on number of items procured. By price discount, we mean that the suppliers provide inventory at price lower than the per unit price on single item purchase. Price discounting may be an attractive strategy for both supplier and purchaser. For the supplier, the price discount encourages fast movement or turnover of inventory to next distribution channel. This in turn lowers the carrying cost of the supplier. Availing price discount on bulk purchase may be an attractive strategy for the buyer, but it should be decided only after proper evaluation regarding trade-off between higher carrying cost and less unit price. To increase sales, many companies offer quantity discounts to their customers. A quantity discount is simply a decreased unit cost for an item when it is purchased in larger quantities. It is not uncommon to have a discount schedule with several discounts for large orders. A typical quantity discount schedule is shown in the table. In column 1, we have shown the discount number 1, 2 and 3. Column 2 shows the discount quantity 0 to 999, 1000 to 1999 and 2000 and above. Column 3 shows discount 0%, 4% and 5%. And in the last column, we have shown the discount cost as Rs 5, Rs 4.80 and Rs 4.75 per unit. As it can be seen in the table, the normal cost for the item in this example is Rs 5. When 1000 to 1999 units are ordered at one time, the cost per unit drops to Rs 4.80. And when the quantity ordered at one time is 2000 units or more, the cost is Rs 4.75 per unit. As always, management must decide when and how much to order. But with quantity discounts, how does a manager make these decisions? As with other inventory models discussed so far, the overall objective is to minimize the total cost because the unit cost for the third discount in the table is the lowest. You might be tempted to order 2000 units or more to take advantage of this discount. Placing an order for that many units, however, might not minimize the total inventory cost. As the discount quantity goes up, the item cost goes down, but the carrying cost increases because the order sizes are large. Thus, the major trade-off when considering quantity discounts is between the reduced item cost and the increased carrying cost. Recall that we computed the total cost, including the total purchase cost for the EOQ model as follows. Total cost is equal to total ordering cost plus total carrying cost plus total purchase cost. Quantity discounts are often offered for extremely purchased items in order to encourage buyers to purchase more units of an item. In such a situation, it is necessary to evaluate the economic trade-off between the savings in purchase cost and ordering cost and the increased cost of holding inventory. Quantity discounts are usually offered in one of the following two ways: all units quantity discounts, incremental or marginal unit quantity discount. Assumptions are as follows. demand is known and constant, shortage is allowed, replenishment is instantaneous. The models in this case will be different because the purchasing price, which is now variable of inventory items, is also included in the determination of total inventory cost. In this session, we will discuss the calculation of the EOQ when price discounts are available, keeping total inventory cost to its minimum. Four steps to analyze quantity discount models. Let us now discuss the 4 steps to analyze quantity discount models. Step 1. For each discount price, calculate a Q star value using the EOQ. In quantity discount EOQ models, the unit carrying cost, that is CH, is typically expressed as a percentage I of the unit purchase cost P. That is, CH is equal to I into P as discussed. As a result, the value of Q star will be different for each discounted price. Step 2. For any discount level, if the Q star computed in step 1 is too low to qualify for the discount, adjust Q star upward to the lowest quantity that qualifies for the discount. For example, if Q star for discount 2 in table turns out to be 500 units, adjust this value up to 1000 units. The reason for this step is the total cost curve for the discounts shown in table is broken into 3 different curves. There are separate cost curves for the first, 0 less than equal to Q less than equal to 999. Second, 1000 less than equal to Q less than equal to 1999, and third, Q greater than 2000 discounts. The diagram shows the various cost curves. When observed, we see that the total cost curve for discount 2, the Q star for discount 2 is less than the allowable discount range of 1000 to 1999 units. However, the total cost at 1000 units, which is the minimum quantity needed to get this discount, is still less than the lowest total cost for discount 1. Thus, step 2 is needed to ensure that we do not discard any discount level that may indeed produce the minimum total cost. Note that an order quantity computed in step 1 that is greater than the range that would qualify it for a discount may be discarded. Step 3. Using the total cost equation, compute a total cost for every Q star determined in steps 1 and 2. If a Q star had to be adjusted upward because it was below the allowable quantity range, be sure to use the adjusted Q star value. Step 4. Select the Q star that has the lowest total cost as computed in step 3. It will be the ordered quantity that minimizes the total cost. EOQ model with all unit quantity discounts. In this case, price is applicable to all units purchased. If there are several price breaks, say 0, B1, B2, B3 up to BI, and the ordered quantity Q lies in the discount interval, say BI minus 1 less than equal to Q less than equal to BI, then the price per unit for Q units is CI, where CI less than CI minus 1. Therefore, the total annual cost for a discount schedule that has price breaks at specified quantities includes the item costs as follows. TCI is equal to DCI plus D by Q into C naught plus D by 2 into CH is equal to DCI plus D by Q into C naught plus D by 2 into Ci into R. For each value of I, a separate cost function for each unit price or each discount range can be defined. The figure represents the total annual cost function TC of Q for any purchase quantity Q in the range 0 less than equal to Q less than infinity. The broken line segments indicate value of TCI beyond their prescribed range for Q and hence have no physical significance. The figure also exhibits different interesting characteristics of the curves at different discount levels, like the total cost curve is made by connecting portions of 4 different continuous curves. Each of the curves, that is the dotted line and the bold portions, is the TC curve that would result if all units cost C1, the next line if all units cost C2, and so on. Obviously, these cost curves do not intersect each other because Ci less than Ci minus 1. Since the total cost curve is discontinuous, therefore the calculus method for finding minimum value of TC cannot be used. Thus, to ensure that minimum cost has been found, it may be necessary to solve the TC equation a number of times, perhaps one for each possible item cost. However, an easy method to find optimal order quantity Q star, which gives the minimum total annual cost TC, is stated below. TCI star Q is equal to total purchase cost of the item plus total minimum variable inventory cost is equal to DCI plus TVC star is equal to DCI plus square root of 2DC naught into R into CI. Now next, coming to models with one price break. Suppose the following price discount schedule is quoted by a supplier in which a price break, that is quantity discount, occurs at quantity B1. This means the optimal purchase quantity can be determined by the following procedure. In the table, first column represents the quantity and second column represents the price per unit. The algorithm. Step 1. Consider the lowest price, that is C2, and determine Q2 star by using the basic EOQ formula. Q star is equal to square root of 2DC naught by C2 into R. If Q2 star lies in the prescribed range, B1 greater than equal to Q2 star, then Q2 star is the EOQ, that is Q star is equal to Q2 star. The optimal cost TC star associated with Q2 star is calculated as follows. TC star equal to TC2 star is equal to DC2 plus D by B1 into C naught plus B1 by 2 into C2 into R. Step 2. If Q2 star is not equal or more than B1, then calculate Q1 star with price C1 and the corresponding total cost TC at Q1 star. Compare TC B1 and TC Q1 star. If TC B1 greater than TC Q1 star, then EOQ is Q star is equal to Q1 star. Otherwise, Q star is equal to B1 is the required EOQ. Let us now take an example to understand these calculations. The annual demand of a product is 10,000 units. Each unit cost ₹100 if the orders are placed in quantities below 200 units. For orders of 200 or above, however, the price is ₹95. The annual inventory holding cost is ₹10% of the value of the item and ordering cost is ₹5 per order. Find the economic lot size. Now let us take a look into the solution. From the data in usual notions, we have D is equal to 10,000 units per year, C naught is equal to ₹5 per order, R is equal to 10% of price of an item, which is equal to rupees 0.10. The unit cost for the range of quantities is given below. For quantity 0 less than equal to Q1 less than equal to 200, the price is rupees 100, and for quantity of 200 less than equal to Q2, the price per unit is rupees 95. Then we will calculate the optimum order quantity Q2 star based on price C2, which is equal to rupees 95, is given by Q2 star is equal to square root 2 DC naught by C2 into R is equal to square root of 2 into 10,000 into 5 divided by 95 into 0.10 is equal to 103 units approximately. Since Q2 star is not 200 or more than 200, therefore, calculating Q1 star, we will get Q1 star is square root of 2 DC naught by C1 into R is equal to 2 into 10,000 into 5 divided by 100 into 0.10 is equal to 100 units. Comparing TC Q1 star, which is equal to 100, and TCB is equal to 200, we will calculate the total cost, that is TC Q1 star is equal to DC1 plus D by Q1 star into C naught plus Q1 star by 2 into C1 into R, which is equal to 10,000 into 100 plus 1000 by 100 into 5 plus 100 by 2 into 100 into 0.10 is equal to rupees 10 lakh 1000. Calculating TCB is equal to DC2 plus D by B into C naught plus B by 2 into C2 into R is equal to 10,000 into 95 plus 10,000 by 200 into 5 plus 200 by 2 into 95 into 0.10 is equal to 10,01,250. Since TC Q1 star less than TCB, therefore, the optimal order quantity is Q star is equal to Q1 star is equal to 100 units. Now coming to the second example. A factory requires 1500 units of an item per month, each costing rupees 27. The cost per order is rupees 150 and the inventory carrying charges work out to rupees 20% of the average inventory. Find the economic order quantity and the number of orders per year. Would you accept a 2% discount on a minimum supply quantity of 1200 units? Compare the total cost in both the cases. Now coming to the solution. From the data of the problem, we have D is equal to rupees 1500 units per month or 18,000 units per year. C naught is equal to rupees 150 per order. C is equal to rupees 27 and R is equal to 0.20. When no discount is offered, the optimal order quantity is given by Q star is equal to square root of 2 DC naught by C into R is equal to square root of 2 into 18,000 into 150 by 27 into 0.20 is equal to 1000 units. Also, the number of orders per year are given by N is equal to 12 into D by Q star is equal to 12 into 1500 by 1000 is equal to 18 per orders per year. Hence, the total cost is TC of Q star is equal to DC plus D by Q star into C naught plus Q by 2 into C into R is equal to 18,000 into 27 plus 18,000 by 1000 into 150 plus 1000 by 2 into 26,460 into 0.20 is equal to rupees 4,81,705.20. Since the total cost after accepting the offer of 2% discount is less than the previous one, therefore, the discount should be accepted. Now coming to model with two price breaks. Suppose that the following price discount schedule is quoted by a supplier in which a price break or quantity discount occurs at quantity B1 and B2. This means the quantity is 0 less than equal to Q1 less than B1, the price per unit being C1. Then we have the quantity B1 less than equal to Q2 less than B2, the price being C2, and B2 less than equal to Q3, quantity with price per unit as C3. Notice that C3 is less than C2 is less than C1. The algorithm. Step 1. Consider the lowest price, that is C3, and determine Q3 star by using the EOQ formula. If Q3 is greater than equal to B2, then EOQ Q star is equal to Q3 star, and the optimal cost TC Q3 star is the cost associated with Q3 star. If Q3 star is less than B2, then go to step 2. Coming to step 2. Calculate Q2 star based on price C2. Compare Q2 star with B1, and if B1 is less than equal to Q2 star less than B2, then compare TC Q2 star and TC B2. But if TC Q star is greater than equal to TC B2, then EOQ is equal to B2. Otherwise, EOQ is equal to Q2 star. If Q3 star is less than B1 as well as B2, then go to step 3. Step 3. Calculate Q1 star based on price C1 and compare TC B1, TC B2 and TC Q1 star to find EOQ. The quantity with the lowest cost will naturally be the required EOQ. Let us take an example to understand the concept. A shopkeeper estimates the annual requirement of an item as 2000 units. He buys it from his supplier at a cost of rupees 10 per item, and the cost of ordering is rupees 50 each time he orders. If the stock holding costs are 25% per year of stock value, how frequently should he replenish stocks? Further, suppose the supplier offers a 10% discount on orders between 400 and 699 items and a 20% discount on orders exceeding or equal to 700. Can the shopkeeper reduce his cost by taking advantage of either of these discounts? Now coming to the solution. From the data of the problem, we have D is equal to 2000 units per year, R is equal to 0.25, C is equal to rupees 10 per item, C naught is equal to rupees 50 per order, and CH is equal to C into R is equal to 10 into 0.25 is equal to rupees 2.50. When no discount is offered, the optimal order quantity is given by Q star is equal to square root of 2 DC dot by CH is equal to square root of 2 into 2000 into 50 divided by 2.5 is equal to 283 units approximately. Also, the number of orders per year is given by N is equal to D by D star is equal to 2000 by 283 is equal to 7 orders. The total inventory cost is given by TC is equal to DC plus D by Q star into C naught plus Q star by 2 into CH is equal to 2000 into 10 plus 2000 by 283 into 50 plus 283 by 2 into 2.5 is equal to rupees 20,707.10. When quantity discount are offered, the following information is available. For a quantity of 0 less than Q1 less than 399, the price would be rupees 10 per unit. For a quantity of 400 less than equal to Q2 less than equal to 699, we will get 10% discount, that is a price of rupees 9 per unit. And for a quantity of 700 less than equal to Q3, we get a discount of 20%, which gives a price of rupees 8 per unit. The optimal order quantity Q3 star based on price C3 is equal to rupees 8 is given by Q3 is equal to square root of 2 DC naught by CH is equal to 2 into 2000 into 50 by 8 into 0.25 is equal to 316 units approximately. Since Q3 star lies in the first range, we need to compare TC Q1 star, TC B1 equal to 400 and TC B2 equal to 700 with each other. TC Q1 star is equal to DC1 plus D by Q1 star into C naught plus Q1 star by 2 into C into R is equal to 2000 into 10 plus 2000 by 283 into 50 plus 283 by 2 into 2.50 is equal to rupees 20,707.10. TCB1 is equal to DC2 plus D by B1 into C naught plus B1 by 2 into C2 into R is equal to 2000 into 9 plus 2000 by 400 into 50 plus 400 into 2 by 2.50 is equal to rupees 18,700. TCB2 is equal to DC3 plus D by B2 into C naught plus B2 by 2 into C3 into R is equal to 2000 into 8 plus 2000 by 700 into 50 plus 700 by 2 into 2.50 is equal to rupees 17,017.85. Since TCB2 equal to 700 is the lowest cost, therefore the optimal order quantity is Q star is equal to B2 is equal to 700 units. Hence, the shopkeeper should accept the offer of rupees 10% discount only because in this case his net saving per year would be rupees 20,707.10 minus 17,017.85 is equal to rupees 3,689.25. Now coming to the summary. Here's a summary of our learning in this session, wherein we have understood the use of inventory control models to determine how much to order or produce and when to order or produce, and also about the inventory models that allow quantity discounts. Thank you.